sent that video specifically and tagged you that please see this last part and come, because today's class will go inside your head only if you are knowing the basics of Lenz's law, otherwise it will become difficult to understand. It's a simple concept, but you should understand how it happens. So, if I once again just give a quick recap about the previous class before winding off chapter number 4 and starting chapter number 5, I encountered one topic from chapter number 6, which is Lenz's law. I said principle of electromagnetic induction found by Mr. Michael Faraday. He said that whenever there is a change in magnetic field or magnetic flux, there is an induced EMF, and direction of induced EMF was given by Lenz. And what did Lenz say? Lenz said that direction of induced EMF will be in such a way that it will always oppose the cause of it. So, if the cause is reduction in magnetic field, the induced current will try to increase the magnetic field. If the cause is increase in magnetic field, induced EMF will try to reduce the magnetic field. That is the Lenz's law concept. I gave some questions also. Even NCERT, an example we saw, I told you if the loop is moving inside the magnetic field, going outside the magnetic field, how does the direction of induced current get decided? I have taught to you in the previous class. Today, we are going to start talking about chapter number 5. I said you this chapter has two parts. One part is all about the properties of bar magnets, that is what is pole strength, what are the properties of magnet like directive property, attractive property and all these things. And then we have the poles, dipole moment and how all these things are derived, mathematical part of this chapter, which I will be doing today in the second half. And the second part of the chapter was about magnetic materials. So, in the previous class, I started talking to you about that, isn't it? So, we will do that part first, and as per the book, we will do the second half first, then we will come back to first half. Okay, there is no reason for that, just because I started teaching about this topic first, I will do it that first. Okay. So, today we are going to learn in detail something very important, which is not given very clearly in NCERT book also, and difficult for you to find in any other book also, about diamagnetic properties, diamagnetism, paramagnetism and ferromagnetism. We will go one by one about each type of magnetism. We will learn about the electron theory, and we will learn in detail about all these effects, how it is coming. So, please pay attention. Notes you will always get, videos will always be there. What thing is, listen, understand, any doubts you can ask me, clarify it. Okay. So, I said I asked a question in the last class. I asked a question like, what do you feel is magnetic? I got your inputs and I told you that don't think like only the things which get attracted by magnets are magnetic. Even you, me are magnetic, even the water is magnetic, even the food is magnetic, even the wood is magnetic. So, everything around us is magnetic. So, as per the theories of magnetism, organic things, metals, non-metals, almost all the materials shows magnetic behavior. And I even said you an example, which you can do at home also, that if you take a thermocol, in that you keep a test tube, put some water inside a test tube, and then you bring keep in the water tub and you bring a magnet near to it, the test tube will start to get repelled, isn't it? So, I said about this. Amrita Varshini, if you are hearing me, the video should be on. This is the first class of you, if I am right. If you are hearing me, Amrita, this is the first class for you, right? Yes, we are in chapter number 5 for your knowledge. Which school you are? SSM school, right? Yeah, they are in which chapter now? Chapter number 4 in your school? 3, 4. Loudly. Yeah, but we are in the introduction of chapter number 5 now. Okay, so please pay attention and try to understand how much you are understanding. Let us see that. So, I was saying that about the magnetic materials. So, I said almost all the things. One example, as I told you about the test tube, it will show some repulsion towards the magnetic field. One more example can be, which you cannot do in the home, but you can do in laboratories if you get a chance, or you can see videos on the YouTube, many videos are there. What do you think? Even the gases show magnetism, oxygen, nitrogen gases are there, no? They show magnetism. Actually, everything shows. They will also show. If you have magnets and if you pour oxygen gas, liquid oxygen or liquid nitrogen, you will see that it gets attracted in the magnets. Now, what is the cause of the attraction by gases? What is the cause of magnetism inside human beings? What is the cause of magnetism inside the water? Everything will be clear to you today. Okay? So, I said to you in the previous class that everything is made up of atoms. I hope everybody knows this. Everything around you, whether it is a metallic thing, a non-metallic thing, an organic thing, whatever you have around you is made up of atoms. And when I speak the word atom, it has electrons inside, isn't it? Now, there are two possibilities. One possibility is, for a particular atom, all the electrons inside the atom are paired electrons. Possibility is there, limited number of atoms, but we have atoms having fully filled electrons. So, every orbital will have 2 electrons inside. I hope you know this SPDF theory and all these things, right? Basic chemistry, where if suppose you have shell like this, then this is kind of fully filled orbital, isn't it? If I am right. So, opposite spins are there. So, this is all the electrons are paired in this element. There are elements where it is not paired, it is like this, unpaired electrons are there. Now, by learning the 4th chapter, you know very well that whenever we have a current, we have a magnetic field. We have current, we have magnetic field, and the current can come by the movement of charged particles. So, there is a single electron which is revolving, it is going to create current, and current in this path will create some magnetic field. That is known to everybody. So, it is quite understandable that if you have a single lone pair of electron, if we have lone pairs of electron in an atom, those single lone pairs of electron are going to create some kind of magnetic moments, right? And those magnetic moments are going to create some kind of magnetism inside. Our brain can accept it. Lone pair is having some magnetic field around it, and that magnetic field can be felt by us. So, the elements or the materials which are having unpaired electrons showing magnetic behavior is quite understandable by us. Problem is, the materials, the atoms which have all the paired electrons, they also show magnetism. That is what hurts us. That is what makes us think how it is possible. Because if you have paired electrons, it is something like this. There are 2 electrons moving in opposite direction, if I am right. One will have clockwise spin, one will have anti-clockwise spin, isn't it? That is why we draw up and bottom. So, clockwise spin, anti-clockwise spin. So, this both spins will cancel each other, right? In the last class, I told this also to you, that if suppose you are having a clockwise spin, it behaves like south pole of the magnet. If you have anti-clockwise spin, it behaves like north pole of the magnet. I told this or not in the previous class? I told this to you, check your notes. So, if you have one electron moving in the clockwise direction, it is going to behave it like south pole. If you are going to have one electron moving in anti-clockwise direction, it is going to make it behave like a north pole. But if you have 2 electrons, one is moving in north, one is moving in south, they will cancel each other. The magnetic moment will become once again 0 because they are opposite to each other. Then why does it show magnetism? Let us see, understand that. So, I told an experiment, and with the help of the same experiment, I will make you understand. So, I said to you, in test tube, if you have water, okay. So, in this test tube, if you have water, and when I bring a magnet towards it, the moment I am trying to bring a magnet towards it, there are 2 possibilities. Either north pole is towards the test tube or south pole is towards test tube, whatever it may be, whether north is towards or south is towards, never matters. What matters is what happens to these paired electrons when the magnet is coming near to it. So, what happens, you see, I said to you, I am talking about the paired electrons. These paired electrons are having opposite spins. So, one electron is moving in clockwise direction, one is moving in anti-clockwise direction. The clockwise direction is behaving like a south pole, anti-clockwise is behaving like a north pole. When the magnet is coming near to it, don't you think, suppose I am bringing north pole this side and south pole this side, don't you think as the magnet comes near to it, since the magnetic field lines are changing in these loops, there will be an induced current? I told in the previous class to you, whenever there is a change in magnetic flux, there is an induced current, and direction of induced current will be in such a way that it opposes the cause of it. So, you see, you will understand now, when the north is coming near these two loops, loops means current moving in circular paths, the south, what will be the net effect? It will try to repel it, isn't it? For repelling it, it has to become north pole. So, south encountering north will make it weaker, it will become less of south, and north becoming north will become a powerful north. I am telling in layman's word. What will be the result of this? This will have a bigger, magnetic moment, and this will have a smaller magnetic moment. Now, net magnetic moment is not zero. I will repeat what I have said now. The moment the magnet is coming towards this paired electrons, one pair was moving in south direction, that is creating a south pole. One was moving in anti-clockwise direction, creating a north pole. But forget about the south-north. Imagine there are two loops. When you have a magnet coming inside these two loops, then the direction of induced current in these two coils will be in such a way that it will oppose the cause of it. Cause here becomes increase in magnetic field. What will be the opposition towards it? Decrease the magnetic field. To decrease the magnetic field, it has to become north, net north. If it becomes net north, south's effect will reduce, but north effect will increase. So, now there is a net magnetic moment. This net magnetic moment is more north, it will start repelling the magnet, isn't it? That is why the water gets repelled. So, basically, the repulsion of water by a magnet is due to Lenz's law, is due to the principles of electromagnetic induction. Are you getting what I am trying to say? When a magnetic material is brought near paired electrons atom, then the magnet coming near to it will start creating an effect where it will start to increase the magnetic field. Now, increase in magnetic field will lead to creation of current in such a way that it will try to reduce the magnetic field, and when the magnetic field wants to reduce, it has to become, in this case it has to become net north, and if it wants to become net north, this north will become more of north, the south will become less of south. In simple words, net magnetic moment is there, which is repelling this existing magnetic field, because north will repel each other, and that is why the water gets repelled. This phenomena is known as diamagnetism. Whatever I told now, you will not find in many books about diamagnetism. So, understand the concept of diamagnetism. What they will talk about diamagnetism in books? Diamagnetism is shown by paired electrons, atoms of paired electrons. The cause of diamagnetism is electromagnetic induction and Lenz's law. But how? Nobody will tell you. I try to tell you. I don't know how much you understood it. Same way our body, human body also, we are organic. Paired electrons are there. When I bring a magnet towards me, my body will create a dipole moment in such a way that it will try to oppose it. In normal state, net magnetic moment of human body is 0, because paired electrons cancelling each other. But when I encounter a strong magnetic field in front of me, net magnetic moment inside me will not remain 0. It will try to repel it, and for that in my body I will have small dipoles getting created. That is why it is said that to strong magnetic fields you should not be subjected to strong magnetic fields. Strong magnetic fields can change the magnetic moment of your body for a while, but it disturbs the whole equilibrium of the body. It is not safe for you to undergo or to be in front of strong magnetic field for a long time. So, which material shows diamagnetism? Many materials show. Organic material shows. water shows, just now I told, isn't it? So these are the things which are showing diamagnetic properties. So diamagnetism, and I hope you understood how it works, at least the basics of it. Okay, I'll give time for writing, but before I go to, I'll give time for you to copy anything from the board. Let me talk a bit about paramagnetism also. Later I'll talk about diamagnetism. In this board, let me talk about at least diamagnetism and paramagnetism. Now, what is paramagnetism? Diamagnetism was due to paired electrons in the atom. Paramagnetism will be due to unpaired electrons. Quite understandable. Why? Because if you have unpaired electrons, these unpaired electrons will create magnetic moment. Common sense. By default, it will create magnetic moment. If it is going to create magnet, suppose I am having a material here and it has unpaired electrons. These dipole moments will be there, but will it show magnetic properties? Suppose I am having, I'll tell the example to you. Good example of paramagnetic material is aluminium. Example I'll tell, it is aluminium. Now, if you take aluminium, will aluminium have magnetic properties? Will aluminium be magnetic in nature? No way. If aluminium is there, and this is aluminium, is it magnet? No. It is not magnet. Why it is not magnet? Because though it has lone pair of electrons, it is creating magnetic moment, but these magnetic moments are randomly oriented, creating a net effect to be how much? 0. Please understand the logic. If you have one electron or one part of aluminium which has only one lone pair, it will show magnetic properties. But if you have material made up of aluminium, it will not show any magnetism because the magnetic moments are randomly oriented, net effect is still 0. I hope you are getting my point. But the moment it is subjected to an external magnetic field, imagine I am giving an external magnetic field here, what will happen? You know very well, if you have magnetic moments, very similar to first chapter, when you have electric dipoles kept in electric field, align the dipoles, right? Same way, when you have magnetic dipoles placed in uniform magnetic field, will align the dipoles. So these dipoles will start to align, and what will be the effect? You know, it will look something like this, little bit improved. So you know what will happen? It will have some magnetic properties now. So now it starts to become magnetic in nature. So aluminium without any magnetic field has no magnetic properties, but the moment you subject a strong magnetic field to it, it will show some magnetic properties. But you will feel, but it never attracts the magnet because it is very weakly attracted by the magnetic field. That much weakly attracted that it is not even felt by you. If you have aluminium, you have a magnet, do you think it will attract it? No. But if you have very strong magnet, you can see some kind of little bit attraction towards magnet, because it is very weakly attracted by the magnetic field. Whereas in the case of diamagnetism, it is not attracted itself. So if I write one point here, it repels the magnetic field, isn't it? Difference between dia and para, you are understanding? It is repelling the magnetic field, but it is attracted by the magnetic field. Another thing I want to say you, if you give some temperature, so due to increase in temperature, what will happen? It will decrease the diamagnetism. Common sense, if temperature is increased, particles will start vibrating. More random motion. If it is having more motion, it will be more difficult for you to align it. So at higher temperatures, due to the increase in temperature, the paramagnetic properties will reduce. Paramagnetism will reduce. But what about diamagnetic materials? No effect, no effect, no effect. How it will affect? There is any temperature involved here? Any electrons involved here? No. No lone pairs involved here, no. So there is no lone pairs involved here. It has no effect of temperature. No effect of temperature. Always remember this. Now I will tell one more interesting thing. Please pay attention. Now we came to know that diamagnetic properties are having paired electrons. Paramagnetic materials have unpaired electron. Since we have unpaired electron, we have magnetic moment here. We have all paired electron, we have no magnetic moment here. But still, why it repels the magnetic field? Because when you bring a magnet near to it, because of the principles of electromagnetic induction and Lenz's law, there is a opposing EMF created, opposing magnetic field created, which will repel the magnets. That's why it is repelling the external magnetic field. There is no effect of temperature on the diamagnetic substances, but paramagnetic substances will get affected, because paramagnetic substances, when you bring external magnetic field, the magnetic dipoles arrange themselves in the same direction, creating some magnetic field. So now it has some weak attraction towards the magnetic field, but when the temperature is increased, the dipole starts to have more random motion, which will once again make it difficult for the dipoles to align itself, so diamagnetic properties will reduce. But think about one thing, don't you think that almost many elements which are having unpaired electrons will also have some paired electrons? Copper, it has unpaired electron. Does it mean it is not having paired electron? It has paired electrons also, no? Those who know chemistry basics, they may understand that elements which have unpaired electrons will have paired electrons also. And paired electrons give rise to diamagnetism. That's why diamagnetism is called a universal phenomena or universal property. Remember this point. Diamagnetism is universal property. This question has come in the board examination also. It means a material having paramagnetism will also have diamagnetism. Once again, I will come back to you. Then why it shows paramagnetic behavior? Because its paramagnetic properties are more than its diamagnetic properties. There are elements like copper, I will give example as copper, whose diamagnetic properties are more than paramagnetic properties, they will be diamagnetic in nature. Are you getting my point? There are elements, there are atoms which are having paired as well as unpaired electron. So now there is a fight between diamagnetism and paramagnetism. If paramagnetism is stronger, it will become a paramagnetic substance. If diamagnetism is stronger, even after having unpaired electron, it will be in diamagnetic category only, which is shown very well by copper, not only copper, gold also. Gold is AU, right, if I am right. Gold shows diamagnetic behavior because its diamagnetic properties are stronger than its paramagnetic properties. Ferro is a different world, I will talk about ferro. First, I hope you are clear in diamagnetism and paramagnetism. There are a lot of difference also. If a question comes, write difference between, you can write difference. This is caused by unpaired electrons, unpaired electrons. Effect of temperature, no effect of temperature. Cause is electron theory, here the cause is electromagnetic induction, the principle. Example here will be aluminium, liquid oxygen, liquid nitrogen, all these things are there.
Sir, what about the orientation of diamagnetism?
Orientation of?
Diamagnetism. Here we are not properly oriented.
How you?
Randomly oriented in paramagnetism. Diamagnetism, is there any difference to write?
How this random orientation came? By what?
Dipole.
By lone pairs, right? Do we have lone pairs there? Then where is the question of orientation, Thambi? Are you getting my point? Orientation question comes only if we have magnetic moment existing, no? There is no question of orientation there. Are you getting? So the cause, once again, the cause of paramagnetism is electron theory, arrangement of electron. But diamagnetism is not electron theory. It is electromagnetic induction principles. Yes, Krishna, tell me something if you are asking.
Sir, paramagnetic substances are weakly attracted, no, sir?
Yes.
Due to diamagnetic properties, so they weakly attracted also?
No. I have written here, weakly repels. It repels, but obviously very weakly. Okay, diamagnetism weakly repels the magnetic field. Paramagnetism weakly attracted by the magnetic field. You can write properly in your notebooks. Now you can take 5 minutes of time, copy the notes and write properly in good words. This question comes every year in the board examination about diamagnetism, about paramagnetism, theories based upon it, MCQs. A and R questions, everything comes from here. Until you are very clear in this, you will make mistake here. So in your own words, write all the points that I have told about diamagnetism and paramagnetism. Yeah, please. I'll come to that. That I'll speak in detail. First, know the basics. Then I'll come to that chi and mu r.
Sir, for diamagnetism, do we have many options definition?
Definition you can do by right by your own. Diamagnetism is a property by which the elements having paired electrons weakly repels the external magnetic field. Yes, tell me, Shweta.
So near that in the diamagnetism you have drawn that south and north now, like clockwise and anti-clockwise.
Yes.
Below that is written the right side. Below that you have written CW and ACW. What is that, sir?
Clockwise and anti-clockwise.
Okay. Okay.
One electron is moving clockwise, one is moving anti-clockwise.
Okay.
If you are done, I will proceed for ferromagnetism. Can I proceed? Green signal from your side?
Sir, I have one general doubt.
Ask me, Yogit.
Sir, if magnetic field is created by current going on, sir, that is because of movement of charge or acceleration of the charge.
You are saying that the magnetic field produced by the current carrying conductor, whether it is because of the movement of charge or acceleration of charge, only by the movement of charge. If acceleration is there, then it will create magnetic field as well as electric field parallelly, which will create electromagnetic wave. So, accelerating charged particles lead to creation of electromagnetic waves, which are the combinations of electric field and magnetic field. But for magnetic field to be created, we just need the particle to move, need not to be accelerated. Are you getting a point? Yes. Anybody has any problem? Can I go to the next point? Shall I talk about ferromagnetism? I hope I can. If you allow me, give the heading as ferromagnetism. Please fast. Give the heading as ferromagnetism. We learnt about dia, we learnt about para. Now I am going to talk about ferromagnetism. I will give time for writing. Please pay attention, become clear in this concept. Before it becomes a disturbing point for you, become very clear in this concept. Please, please. Yes. So now, what is this ferromagnetism? So, as the name says, ferro, it comes from where? Iron. So, example of this is going to be what? Iron, cobalt, nickel. There are only three elements which shows ferromagnetism: iron, cobalt and nickel. Okay. What is so special about these three elements? So, I said you before some days when I was teaching you previous chapter itself, that in the previous chapter we learnt about magnetic field by current carrying conductors, but it does not mean that we do not have natural magnets. We have natural magnets also. And where do we find it? In earth crust. By mining we can take out something, some lodestones, right? We get it in the Magnesia Island. First time we got it from Magnesia Island. But have you ever thought that when we get something from the earth's core, it will be iron only, no? Does it mean that all the iron that we find inside the earth is magnet? But why some of the iron becomes magnet? Which iron becomes magnet? How does it become magnet? Let us learn today. So, by nature, elements like iron, cobalt and nickel, they show some behavior, very, very peculiar behavior. They also have unpaired electrons. Their unpaired electrons are also randomly oriented. But you know how? See, you will understand. What did you understand? Yes, good word. Somewhere you have heard about it already, Mr. Sharan Ram. Good. It's about domains. Domains are the collection of electrons, I should not say electrons, the unpaired electrons, which are having magnetic moments in a particular direction. So, overall, whether this material will have magnetism? No, because cancelling out each other. But if I take a domain alone, it will be magnetic in nature. So, what do you want for a magnet to be naturally occurring? You want all the dipoles to be in the same direction. And all the dipoles in the same direction is called as one domain. What is the name of this? It is called as domain. So, in ferromagnetism, we have something called as domain theory. What is domain theory? A part of the ferromagnetic substance which has all the magnetic dipoles aligned in the same direction. But in a particular rock of iron or a piece of iron, we may have hundreds of domains, but each domain will not be in the same direction. But somehow, naturally, if you get a particular rock of iron or iron ore you get, where all the domains are in same direction, it will have magnetic property. Have you ever felt that if the natural magnets fell for 10 times, its magnetism will be lost? Those who have played with magnets, they may know this. If your magnet fells for many times, no, it will become weak magnet. If you don't know, you can try it later. Because if it falls down, domains once again gets disturbed. If domains are in same direction, it will have perfect magnetic property. If it is in random direction, it will once again become a non-magnet substance. I hope you get what I am trying to say. So the reason of magnetism inside iron, nickel, copper, not copper, cobalt, is because of domain formation. And now imagine domains are there, it is subjected to external magnetic field. The moment I subject it to external magnetic field like this, what is going to happen? A strong magnetic field can move the domain itself in a particular direction. Now, my domains will be aligned in what direction? In same direction. What I am going to get? I am going to get a strong magnetic field, because in the case of paramagnetic substance, everything was individual. It was difficult to control individual dipoles. But here we have lakhs of dipole together, thousands of dipole together. Give magnetic field, all thousand will turn together. So easy to create magnetism, right? That is what happens in the case of ferromagnetic substances. The moment you apply external magnetic field, domains get aligned in the direction of magnetic field, creating stronger magnetic field. So you can see very clearly and say they will be strongly attracted. They will be strongly attracted by external magnetic field. Diamagnetic substances weakly repelled. Paramagnetic substances weakly attracted. Ferromagnetic substances strongly attracted. Why also understanding why strongly attracted? Because here domains will align when you are subjected to external electric field, and domains will come in the same direction, leading to the creation of stronger magnetic field. Now please pay attention. What happens at higher temperatures? So it is found that, please pay attention, at higher temperatures, at very high temperatures, for example, for iron it is around 700 something, 730 degrees Celsius. If I am not right, not wrong, I don't know exact value, but some great value only. At very higher temperatures, it has been found that, suppose I am taking a iron and subjecting it to very high temperatures. At very higher temperatures, the ferromagnetic properties, that means the domains, they are broken. This temperature is called as Curie's temperature. It was found by Curie. So Curie's temperature. What is Curie's temperature? Temperature at which ferromagnetic properties are lost. What will happen? It will become paramagnetic. So ferromagnetic substance at very high temperatures. What temperature? Curie temperature becomes what? It becomes paramagnetic. But one more thing I will tell you, please pay attention. The moment once again temperature comes down, it retains ferromagnetic behavior. That is the behavior, quantum behavior of the element. At very high temperature, the domains are going to break. Break in the sense it will disappear and it will behave like paramagnetic substance. But the moment temperature becomes lesser than Curie's temperature, suppose Curie temperature is 730 degrees Celsius, moment it is coming 725 also, it will once again become ferromagnetic. Are you getting my point? So that is the behavior of ferromagnetic substances, and in the whole periodic table only 3 elements, 3 atoms are having this property. I said iron, cobalt and nickel, and that is why they are used in making permanent magnets by solenoids. Solenoid you are keeping, right, that is external magnetic field. Soft iron is going to create temporary magnetism. If you have cast iron, nickel you have, cobalt you have, keep inside, become strong magnet, permanent magnet. Are you understanding what I am trying to say? One more thing I will say. In the case of paramagnetism, the moment the external magnetic field is removed, once again domains will come back to the random orientation, no magnetic properties. But not in the case of ferromagnetism. Even after the removal of external magnetic field, the ferromagnetic property retains. Suppose you have iron nail. You would have seen this in the pin box. Some of you have seen the pin box. You have a box in which magnet is there, inside many pins are kept. That pin if you take out also, it will have some magnetic behavior for some time, because ferromagnetic property retains even after the removal of external magnetic field. But paramagnetic properties are lost the moment the external magnetic field is removed. If you have understood this theory, copy it up, whatever you want to write from here also. Then I will talk about the mathematical part of it. Please tell me, Krishna.
Sir, you said that at high temperature, at Curie temperature, ferromagnetic properties will become as paramagnetic
Yes,
properties. Sir.
yes.
So, same as for paramagnetic properties, if I cool the temperature up to minus Kelvin.
Minus Kelvin is not possible, man. 0 Kelvin is the lowest temperature possible. But yes.
No, sir.
Minus.
Up to something minus degree Celsius.
Yeah. Understood what your point is. You are trying to say that if paramagnetism is too much cooled down, whether it will become ferromagnetic in nature, that is the question, right? No. Answer is no, because paramagnetic materials will never get domains formation. Domain formation happens only in iron, nickel and cobalt. So they can never become ferromagnetic. But one thing we can do, as you are saying, at lower temperatures, their paramagnetic properties will become stronger. If you compare aluminium at 100 degrees Celsius, aluminium at minus 100 degrees Celsius, and both of the aluminium is subject to magnetic field, then minus 100 degrees Celsius aluminium will have a better paramagnetic properties compared to 100 degree aluminium. Are you getting my point, Krishna?
Yes, sir.
Yes. Copy it down, everybody, please, fast. Whatever you want to copy, first copy. Shweta, you can mute yourself.
Sir, I want to ask something. Sir, in case of diamagnetism,
Yes.
you said it is weakly repelled.
Yes.
So can that also be called as strongly attracted?
So you think that weakly repelled means strongly attracted? It's not truth table, man. Weakly repelled means weakly repelled only. Where did I say strongly attracted? Weakly repelled means it is weakly repelling the magnetic field. Are you getting, Shweta?
Yes, so it will not be attracted at all.
Never. A diamagnetic property will always repel only the magnetic field. Para will weakly attract, ferro will strongly attract. I hope you got it.
Yes.
Yeah.
Sir,
Please tell me, Shaktivel.
so then is this also why a piece of iron would give off a magnetic field when current is passed through it, sir?
If you pass current through an iron substance, then what will happen? It will have current around it. If current is there around it, it will create a magnetic field around it, isn't it? That magnetic field may induce magnetism inside the iron and may make it more magnetic in nature. But generally we don't do that. See what we do, we have a solenoid, right? By this we create magnetic field artificially, because it has the very good amount, bar magnet resembling magnetic field. Inside, if I want to have a temporary magnetism, we keep soft iron core. Suppose I want to make a solenoid which should have a temporary magnetism, then I will keep a soft iron core. Suppose I want to make magnets for commercial selling, then I will take nickel, iron, copper, and using solenoid I will make permanent magnets. Don't think that for taking out the magnets that we are using in the industry, we are always digging the earth and taking out the magnets. No. We are whatever iron you are having, which is not having magnetic properties also, we use solenoid and make it magnetic. Are you getting my point? Whatever permanent magnets we are using in our daily life, we don't want to dig it out and take from the earth. Whatever iron you have got, even though it is not having magnetic properties, we will make it to get magnetic properties by using solenoid, by giving external magnetic field. I hope you understand this. Okay, is it clear to everybody? If you allow, I will go to the next page now, where I will talk about the magnetic part of this chapter. Sorry, mathematical part of this chapter. Shall I talk about that, which you asked me about chi and mu r? We will talk about that now. Okay, so Let me write. Why para I wrote first here? First is dia only. Diamagnetic, paramagnetic and ferromagnetic. Everybody, I will give time for writing. Please, please, please pay attention. So, I am taking up diamagnetic. For example, I am taking a piece of wood. I am taking paramagnetic substance, I am taking a piece of aluminum, and for ferromagnetic I am taking a piece of iron or cobalt, whatever you want to take. And what I am doing, I am subjecting all these three substances to some external magnetic field. So, imagine that we are going to give some external magnetic field to this diamagnetic substance, to this paramagnetic substance, and to this ferromagnetic substance. I will give time for writing. I said, please pay attention, listen to what I am teaching now. The concept should be very clear to you. So, what I have done, I have taken up diamagnetic substance, I have exposed my diamagnetic substance to external magnetic field. Same I have done for paramagnetic substance, same I have done for ferromagnetic substance. Let me assume that the magnetic field that I am applying externally is B naught. What I am writing now may not match with NCERT, but later you can change it to NCERT form also. Let me teach in my own way. B naught is the applied magnetic field. Okay? Just now I told you by the concept of paramagnetism, diamagnetism, ferromagnetism, the moment you give external magnetic field, there will be an induced magnetic field inside, isn't it? In this case, diamagnetic case, the induced magnetic field will be in the opposite direction. Don't you think so? Because it is going to repel. And here induced magnetic field is going to be in the same direction of the applied magnetic field. And here the induced magnetic field will once again be in the same direction of the applied magnetic field. So, the moment you are applying a magnetic field in the substance, there will be an induced magnetic field. Why? Because of electromagnetic induction principle. Why? Because of electron theory. And why? Because of domain theory. Are you getting why B induced is coming? In this B induced is coming because of the electromagnetic induction principles. Why is magnetic field coming here, inducing here? Because of lone pair of electron magnetic dipole. And why is it inducing here? Domains are present, they will induce magnetic field. Okay. So, net magnetic field will be B naught plus B int. I will talk about that later. But one thing is very clear, that how much is the magnetic field going to induce depends upon how much is the magnetic field applied. Don't you think so? If you apply a stronger magnetic field, I will have stronger induction of the magnetic field. If I am applying a weaker magnetic field, a lesser magnetic field will get induced. If I remove the proportionality sign, I have to add a constant, right? That constant is called as chi, which is called as what? Chi is what? Susceptibility. Already came in the second chapter. Here it is called as magnetic susceptibility. In that chapter, in the second chapter, it was called as electrical susceptibility. So, here we call it as chi B, there it was chi E. So, chi B is called as magnetic susceptibility. Now, since I am applying an induced magnetic field, that is applying a B naught external magnetic field, I am getting an induced magnetic field, and induced magnetic field is trying to repel the applied magnetic field, isn't it? So, if I draw, what will happen? I will draw the lines like this. So, now lines became like this, like little repelling. Are you feeling that? It is trying to repel. Here what will happen? It will have a weak attraction. Attraction will be there, but not that strong attraction, some weak attraction. And what will happen here in the case of ferro? Strong attraction. Are you feeling that? Strong attraction. So, these diagrams I have drawn based upon the theories I have studied before some time. So, in the case of diamagnetic substance, we have weak repulsion. Here we have weak attraction, And what do we have here? We have strong attraction. Now you think and say me mathematically, if it is weak, it means induced magnetic field is going to be small. And how is it possible if chi value is small? And since it is going to be repulsive, it will be negative. So I will write that chi for diamagnetic substance will be negative and small. Small y because weakly, negative y because repelling. Same way you can tell me what will be chi for paramagnetic substance? Small and positive. Y positive because it is attracting, y small because it is weakly attracting. Same way, what is going to be chi for ferromagnetic substance? Positive and large. Why positive and large? Because it is going to be strongly attracted. The word attracted means positive. The word strongly means large. Weak means small. Attracted means positive. Weak means small. Repulsion means negative. Direct question comes from the board examination. Direct question comes from here. They will draw a diagram and they will write how will the chi will be for this. If this diagram is there, you will write chi will be positive and small. For this you will write chi is negative and small. Chi will be negative, positive and large. Direct question comes from here. I am telling you in the board exam. Then you will, if you derive it further, I am deriving it here. I don't have much space. I am deriving it here. Okay, you don't write properly. So I can write total magnetic field will become equal to B applied plus B induced. Can I write like this? Applied magnetic field is B naught, induced is B induced. If I add both, that is total magnetic field. So total magnetic field can be written as B naught plus what is B induced? Chi times of B naught. So B will become equal to 1 plus chi times of B naught. This 1 plus chi is there, no? This 1 plus chi is called as what? Mu. Those who know. Yes, it is called as mu r. Mu r means what? Relative permeability. Relative permeability. So since mu r is 1 plus chi, chi is negative and small. Understand my point? The formula of mu r came to be what plus what? 1 plus chi, isn't it? Imagine chi is negative, so it will reduce the value of 1 and small, which will make my mu r what? Slightly less than 1? Obviously less than 1, slightly less than 1. Here what will happen to mu r? Slightly more than 1. What will happen to mu r here? Much greater than 1. So if I give you a question, relative permeability of a material is 21,576. What is the material? Ferromagnetic. Permeability of a material is 0.992. What is the material? Diamagnetic. 1.063. Paramagnetic. Are you getting? Direct questions will come from here also. They will give a value of paramagnetic, that is mu r, for a paramagnetic substance or diamagnetic substance or a ferromagnetic substance, and they will ask you which material is that. By knowing this, you can easily answer it. Got my point? So mu r less than 1, mu r more than 1, slightly more than 1. Remember that it is slightly less than 1. It is slightly more than 1, and that is much more than 1. If you have understood this, copy it fast. If you have understood the mathematical part of this topic, write it fast. Once again, this Sunday you have test here, those who have seen the timetable. And portion is 1, 2, 3, 4, not this chapter. Portion is 1, 2, 3, 4. 9 itself. Have you copied, all of you? Sure? Yeah, fast one. Obviously.
Because while they're teaching it only within 30 minutes they completed all these things, and just they my sir just wrote the table.
Hmm.
He wrote all the differences and he said that
Mu are more than 1 less than 6 only, no?
nothing he wrote that.
That's what I'm telling. That concept nobody teaches actually. Not now. Last 10 years I am in this field and I am saying this. So I also was not able to do it initially. Then slowly I learned all these things. Because if you read about it, no, books will not have these theories easily. It is domain theory and all is in quantum mechanics only. Something you are asking, Sharon? I hope all of you have copied. Can I proceed further? I hope I can proceed further. Done? Okay. So as of now, what we learnt? We learnt about magnetic substances, isn't it? See, this chapter has only two parts. One part we have done now, which is talking about what is the meaning of diamagnetism, what is the meaning of paramagnetism, what is the meaning of ferromagnetism. I said to you, diamagnetism is that property by which the diamagnetic substances which are having paired electrons inside them are going to weakly repel the applied magnetic field. And why they do so? Because of the principle of electromagnetic induction and Lenz's law, they repel the magnet coming towards it. So I said about diamagnetic substances that they are having paired electrons and they are unaffected by the temperatures, isn't it? And also I told the example of diamagnetic substances which are organic substances, water, even copper, gold, they show diamagnetic behavior. Then I spoke about paramagnetic substances. They are those substances which are having lone pair of electrons and weakly attracted by the applied external magnetic field. So since they have lone pair of electrons, they are going to create magnetic moments by that, and since we have magnetic moment, it is going to create a weak attraction towards the applied magnetic field. Then I told to you that paramagnetic properties are affected by the temperature. At higher temperatures, the electrons becomes unstable, they start vibrating too much, and that leads to decrease in the paramagnetic properties. Also, I have mentioned to you that whenever an atom has unpaired electron, it also has paired electrons, which is the case of copper and gold, where the elements have unpaired electron along with paired electron. So, there it is the dominance of either paramagnetism or diamagnetism that decides whether the element will be diamagnetic in nature or paramagnetic in nature. Same in.
All the paramagnetic elements also are like
Diamagnetic, yes, but everything, but they cannot be called as diamagnetic because their paramagnetism is more than diamagnetism. That's why I used one word. I told that diamagnetism is universal property. This question has come in the board examination. Which is universal property? Diamagnetism, paramagnetism, ferromagnetism, none of these options. Answer is diamagnetism. Why is diamagnetism universal? Because all the elements, even if they have unpaired electron, they will also have paired electrons. But dominance of paramagnetic properties makes the paramagnetic property paramagnetic in nature. So,
Ferromagnetism is also diamagnetic.
yes, it will have. Everything has diamagnetism, I told you no. So, I said you about how like copper and gold, they are having unpaired electrons, but even then they are diamagnetic in nature. Then I taught to you about ferromagnetism. I told ferromagnetism is because of domain theory, where the electrons which are having the same orientation, that is magnetic dipoles having the same orientation, are called as one domain, and here domains are randomly oriented. That's why there is no magnetic field initially, but the moment we subject it to external magnetic field, domains are aligned in the direction of magnetic field, which leads to creation of magnetic field. We have stronger magnetic field created here, so it is strongly attracted by the applied magnetic field. And one more thing I want to say here, that ferromagnetic materials at higher temperature, known as Curie's temperature, lose their domain property and becomes paramagnetic in nature. So, if they ask you at what temperature they lose property, that temperature is called as Curie's temperature. Then I said to you, example of ferromagnetic substances are copper, nickel and cobalt, and then I have drawn this chart table where I have told to you which is weakly attracting, strongly attracting, weakly repelling. How it happens I told you. This logic I told you how these things have been derived. So, chi E is negative and small for diamagnetic substances, positive and small for paramagnetic substances, positive and large for ferromagnetic substances. Apart from that, we learnt about relative permeability mu r, which is slightly more than 1 for diamagnetic substances, slightly less than 1 for diamagnetic substances, slightly more than 1 for paramagnetic substances, and much more than 1 for ferromagnetic substances. So, with this we come to end of this topic. We have to start the next topic, which is about bar magnets and their properties, where we will learn about. Now, what are we going to learn in this chapter is going to be replica of first and second chapter. Remember that. So, I will tell you that what is a bar magnet, and I will relate a bar magnet. You know one thing, this bar magnet, suppose it is having a north pole and south pole. If I ask you, where is the pole located, what is the answer? At the end? Or half is north, half is south? So, if end is only north and south, then what is here? No direction? These things will be clear when I tell you about it. First you understand, now let me tell this to you. These poles are located inside the edges. So, if I am having a bar magnet, north pole's exact position will be little inside the magnet. Here also little inside the magnet. This is called as QM, pole strength, QM. So, QM1 or QM2 you can write, pole strength. So, for a bar magnet it has equal and opposite poles, and this length is called as magnetic length. So, magnetic length is the exact distance between two poles, which is approximately 85% of the geometrical length. Geometrical length, suppose it is 1 meter, then this is going to be 85 centimeter. Approximately, I am not saying exactly. It is magnetized in the sense?
Why is it easily attractable at that point?
Because the magnetic field line starts from one pole, suppose north, and it ends towards south. So, if you draw the magnetic field lines, you will realize that near the poles we have more magnetic field lines, right? Yes, Praveen. Since you have more field lines, suppose I draw a circle here. How many lines you got? 1, 2, 3, 4, 5, 6, 7, 8, right? If I draw same circle here, how many lines I got? 3. If I draw same circle here, I got less line. So if you draw a unit circle, you will realize that you have more number of magnetic field lines at the poles. So it will have strong attraction or repulsion in the poles. And away from the poles, the magnetic field keeps on reducing, so the magnetic properties also reduces. Understanding my point? So this is about the pole strength. So what we are going to learn now, I'm just giving the introduction about the next half of this chapter. We will learn about what is the Coulomb's law between these poles. You have F is equal to K Q1 Q2 by R square, right? Here also you will have F is equal to mu naught by 4 pi into Qm1 into Qm2 by R square. There you learnt about what is electric field. You defined electric field as force per unit charge. Here you will define magnetic field as force per unit pole strength. You learnt there that two equal and opposite charges kept in a small distance creates electric dipole. You will learn here two equal and opposite poles kept in a small distance create a magnetic dipole. It means a short bar magnet is also a magnetic dipole, because they will have opposite poles. If you take a small magnet, bar magnet, it can be called as a magnetic dipole. So what is magnetic dipole? It is arrangement of two poles equal and opposite having a small separation between them. You learned about dipole moment there, electric dipole moment. P is equal to Q into 2D. Here you learn about magnetic moment, which will become equal to Qm into 2D. You learned there about electric field due to electric dipole at an axial point. The value was K into P, 2K P R by R square minus D square. Here you will get mu naught by 4 pi into M into 2R by R square minus D square. For R much more than D, you got there 2K P by R cube. Here also you will have mu naught by 4 pi into 2M by R cube. There you had magnetic electric field due to electric dipole at an equatorial point as K into P by R square plus D square power 3 by 2. Here you will have mu naught by 4 pi into M by R square plus D square power 3 by 2. There you had electric field at an equatorial point where R is much more than D, as electric field value is equal to Kp by R cube. Here you will have mu naught by 4 pi into M by R cube. There you had, if dipole kept in the uniform electric field, torque will act on it, turn it. Torque value is P sin theta. Here you will have same thing when you have a MB sin theta. Same thing you have studied in last chapter also. MB sin theta. We will relate how a solenoid is equivalent to a bar magnet. Mathematically, we will relate here. We will also try to find how the magnetic dipole and electric dipole have analogy, how they are similar to each other. All these things we will learn in the next class. Next class, this chapter will be done, and we will take some questions on the board papers also, how it has come in this chapter. So next class, we will be done with the chapter number 5, we will start chapter number 6. Okay. So today I am ending my class early on the request of many people who have already messaged me, and they told they will not be able to come for the class. Many are absent today for the class. So keeping them in mind, I am giving the class a little early today, ending the class. But I want Amrita Varshini to stay for some time before everybody else leaves. Okay. Take care. Bye bye. We will meet again. Others can drop from the meeting. Amrita Varshini, you can stay back.